Right. Namaste and welcome everybody to the TAI seminar series. This week it is Arpit and I. Arpit and I are going to present this seminar on ensemble quantile-based framework for predicting streamflow extremes using deep learning. And this paper is on arXiv, and it's a multi-author paper. Actually, the work began with Jim from my honors class. So he's an honors thesis student. So he began the work and in collaboration with Willem Verwoerd from University of Sydney. And then the thesis was kind of done, but it wasn't really extended into a paper. Then we had Siddharth Ketkar here from IIT in India, and he did an online internship and that progressed into a paper. So I reran all the code, and then basically I was not very pleased with some of the parts, and then I mean Siddharth did his best, but at that point of time he had to go for a placement. He began his work, and so we were on hold, and then I asked Arpit to help me finish off some of those experiments. So Arpit reran the code and updated things. Anyway, so let's continue. Arpit, next slide, please. So what do we see here? We see floods in Yugora region in New South Wales, November 2022. And we know that that year we had massive floods in New South Wales and also in the state of Queensland. Some of those regional towns, regions had problems, and it was a difficult time. So all this motivated us to get into this research where we could use deep learning and related models to forecast floods and extreme stream flow, which is the focus of this study. Next slide. So I think if you are in Australasia, it's not a flood is nothing new. I mean, especially here in the Pacific in Fiji, we have more floods, probably more often than you have it there in Australia. Our cyclone, we have specific cyclone seasons that go from mid of December to mid of April. But even in the non-cyclone seasons, we get flash flooding. And in Australia, you have more of this flash flooding in the tropical zones, usually less in New South Wales, but in northern New South Wales, which goes more towards the tropical zone, you have more of those cases. So there's a lot of problems when it floods. Of course, you have couple of $1 billion of extreme flood event is economic losses, right? The thing with economics is it's the loss can also be a gain as well. Like, I mean, somebody's loss is somebody's gain when it comes to infrastructure development after floods. So sometimes when there's infrastructures are destroyed, then insurance companies give, if it is insured, and the government take loans and redevelops the place. So economy usually bounce backs, but then there is debt to pay. So the bigger problem is the damage to the natural habitats, wildlife, human lives, psychological effects, of course, people who have suffered from drowning. I mean, I once drowned in a swimming pool. I was about to drown, and it's a horrific experience.
No, still alive.
I'm still alive. My friend pulled me up, but the thing with drowning is like, I mean, we're three of us best friends in the pool, and one of my friend was pulling me up, and I kept pushing him down, and It's just that this, and it's like you are in, and this is like I was 16 years old probably then. But yes, this, I've kind of got out from the psychological effect by now. But there are people who are depressed, they have anxiety disorders. So we need to develop better models for flood prediction and stream flow prediction, which is related to flood. So that's the focus of our study. I repeat, next slide, please. So when we look at floods, for especially when you look at regions in Australia, Australia is a big country, right? So I mean, you could see this, like if you put like hundreds of stations. Station by station we mean a place which has some kind of equipment that collects the data, how much of rainfall is there per day or every hour, right? So those are catchments. I mean, these stations are cover certain catchments, and there are more than 222 of them in Australia. These stations that cover catchments, but it's not, and the data is out there, right? Um, and this traditional, there's a lot of data actually. There's a lot of data, big data problem, because you are looking at daily. Then you are going, if you cover a couple of decades, then you have different. It's not just the rainfall data that you are interested in. You'll have temperature data, you'll have humidity, you'll have pressure, you'll have a lot of other things, and that's a multivariate modeling problem. So that's a challenge. The other challenge is the extreme events. It's extreme event prediction. By extreme means you don't get it every now and then. You get once in a while. It's not, and it's not going to tell you when it's going to come. So these weather conditions, and because of the nature of how it occurs, it becomes difficult for machine learning models, which are more suited to model things that are well known. When we say extreme, we can just say that things that are not really known, and we are anticipating some certain behaviors in the future where we will not really know or cannot know. So that is other problem. The other thing is uh, the uncertainty quantification. Like if we have a model that says that there will be a flood tomorrow, then how certain is it? So if there's some kind of a probability attached to that model, then that would be more useful. So we need probabilities, we need probabilistic models, and uncertainties are very important. So these are some of the challenges that we address in our research. So machine learning in hydrology, it's not new. It's there for a while, right? Hydrology, we're basically dealing with time series forecasting, multivariate time series forecasting problems, related problems, and machine learning has been successful in a lot of fields. And hydrology is also one of the bigger and prominent applications of machine learning. Is there. But when you look at hydrology, you have basically this area where you have econometrics models, you have statistical models that were doing a lot of the time series forecasting work. Machine learning has been prominent, but it's not really that prominent compared to the others. That's one of the things. And in the last 10 years, though, with the rise of machine learning models and deep learning infrastructure, better deep learning algorithms, models, this is becoming more possible. So one of the things is the stream flow prediction. So if you kind of can predict how fast is the stream flow, the rate of the stream flow, then with that you can predict if it is going to flood. And these are coupled together. So, what are some of the advantages of machine learning? It's kind of well known. They are quite of good in nonlinear patterns in data. They can integrate multiple data sources, real-time adaptability, very easy to train when more data gets available. Limitations, lack of interpretability, heavy reliance on the training data, and uncertainty quantification in training um, conventional or traditional machine learning models, such as neural networks. So, in this work, our key research contributions highlighting all those things. We want to address the problem of stream flow prediction and also flood forecasting. So, there are two problems, and if we can solve one problem, then that could lead to solving the other problem. So, we try to do both in this work. So, in order to do that, we know that we need some sort of uncertainty quantification, and that's where we have this quantile deep learning model. And because we are dealing with the regional stations, and we are also dealing with a number of different models, deep learning models, which we compare with, then we eventually develop an ensemble or a group of those models into a quantile deep learning framework. So this is more of a methodology paper in sense that this is pretty new in the sense the way we have incorporated a wide range of models into a quantile deep learning framework, and that could help us to stream forecasts, give uncertainties around those forecasts, from which we can have a flood risk indicator estimation. And we do, in the process, integrate static catchment attributes with dynamic time series data. And we perform multivariate and multi-step streamflow prediction using the CAMELS US dataset, which has some 222 stations. But we do look at select some of those stations to show effectiveness of our model. And finally, as we do in most of our projects, we provide an open source uh, framework and methodology for broader applications and extensions, and of course, reproducibility of results. Art can take over from here.
Thank you, Rohit. So I'll be discussing the methodology that we'll be using in this work. We have used in this work. So because I think it should be clear that we are using machine learning, and the basis for our machine learning model will be quantile regression. So I'll just briefly go over what is the difference between standard regression methods and quantile regression. So quantile regression is different from mean square or sum of squared, least squares method in the fact that instead of learning the mean prediction for the target variable, we are trying to learn the quantile of the target variable, a specific quantile of the target variable, right? So which is conditioned on the inputs and the model parameters, right? So this picture, which I've taken from a really nice blog that I found, it shows the difference between linear regression and a linear regression with quantile regression. In this case, we see that using three different quantiles, learning three different lines, linear lines, for this method, we are able to actually quantify a confidence interval between which we can be 50% confidence at least that the value lies within that confidence range. Right, so how we achieve this is by the means of the tilted absolute value function. But before we get into that, I'll just try to give you a setup of this loss function. Right, so let's assume that y is the real valued random variable, which is the target value that we want to learn the quantile for. Then in that case, the capital F of y is the cumulative distribution function of y, stating that for a given small y, it quantifies the probability that the random variable y will lie under this value small y. right? So for a specific quantile, in this case, which lies between 0 and 1, we can compute the value of y that corresponds to that specific quantile by computing the inverse of this cumulative distribution function, right? So this function q then becomes the inverse cumulative distribution function of random variable y, which is actually computed as the infimum of y where fy is greater than tau, right? So basically, we are trying to find the smallest value of y for which the cumulative distribution function yields the value greater than tau in this case, right? So in order to optimize, so this is the problem that we want to solve for a given y. And the way we do it is with the help of the tilted function shown in equation 2, where the tilted function for a specific tau and a given input m is computed as m into tau minus where 1 is this is the indicator function of m less than 0, right? So what we are saying is, in the case that the input m is positive, the output of this function would be tau minus 1 into m. And in the case that m is less than 0, which means m is negative, the output of this function would be m into tau, right? And when we combine this, when we replace the value m with the residual of our model, where y is the target value and u is the predicted value, we get equation 3, right? And basically in equation 3, we are trying to minimize the tilted absolute value function for the fixed value of tau on the residual, and we're trying to minimize the expected value of this function, trying to find the best u that minimizes the expected value of this function. And when we do this, we instead of estimating the mean value of the y value at a specific time, we actually learn the quantile of the y value, the specific quantile given by tau in this case, right? So we can replace tau with 0.05 for 5th percentile and 0.95 for 95th percentile, and we are able to learn a confidence interval through this method. Right, so the neural networks that we'll be using in this case are based on LSTMs. So this is just an overview of LSTM cell for anyone who isn't already familiar with them. So an LSTM cell represents a layer of neural network where which is a recurrent neural network. This recurrent layer takes a series of inputs spaced out in time. So xt represents the input at time t. The way this LSTM cell works is by updating a constant memory of the cell with each input that comes in. And we update this memory by the help of 3 gates in this model. And the corresponding gates are called the forget gate, input gate, and the output gate. Right, so the forget gate is responsible for removing any previously held information in the cell state C. The input gate controls how much information from the input goes into the cell state when we update the cell state. And the output gate controls how much of the new input and the previous cell state's value propagates into the output of the unit, right? So this way we are able to conserve the information over long sequences of inputs, and we can generate outputs that have a lot more dependence on even very long-term inputs. Right, so based on the LSTM layer, we can create an LSTM neural network, which is the first basic neural network that we'll be experimenting. We have experimented with this application. So the LSTM architecture that we use in this research is a very straightforward single layer LSTM, where a sequence of input represented by xt is passed to the input layer. Then we have an LSTM layer. Finally, a couple of dense layers and output layers transform them into output sequence y. In this case, I have used the same sequence length in input and output, but we can design the model to have a different input and output sequence length as well. Right, and we also experiment with CNN architecture. So we know that 1D CNN convolution neural networks are can actually be useful in time series prediction as well, as shown in previous research. Some of it coming from our group itself. So which is why we also evaluate a CNN-based model where we follow a similar architecture, but instead of using an LSTM layer, we use an embedding layer followed by a 1D convolution layer. The embedding layer here is used to just expand the input to a higher dimension, so that then that can be passed by a convolution layer to compress it into a lower dimension and produce the output. Right, the third model that we are also going to evaluate is what's called the bidirectional LSTM or the BD-LSTM. Bidirectional LSTM, as the name suggests, it's an LSTM based neural network where the information flows in two directions, one in the forward direction and one in the backward direction. So we have two LSTM layers, one which is propagating forward in time, and the second one which propagates information backward in time. And we combine the outputs from these two LSTM layers to generate the final output for the model. And this can, of course, then be followed by some dense layers if required. In this case, I don't think we have used any dense layers in this architecture. Lastly, we are also going to evaluate encoder-decoder based architecture. Since this is sequence-to-sequence prediction, and we know that encoder-decoder models can be really good at learning sequence-to-sequence models, sequence-to-sequence problems. So which is why we are also evaluating encoder-decoding model over here. The encoder-decoder architecture in our case consists of the encoder, which consists of LSTM layers, and in some cases we can also use some dense layers to generate to either reduce or increase the size dimensionality of the features. Then which is followed by the embedding layer, which embedding layer tries to compress the information that we have that is generated by LSTM layer into a very into a smaller dimension input, which is then passed into the decoder set, the decoder layer, which finally again passes the embedded information into the LSTM units, finally producing a sequence of outputs for TYT. Right, so I'll hand over to Rohit to go over the evaluation framework for these models.
Thanks, Arpit. What Arpit has presented are four key models, which are the conventional deep learning models. Essentially, we are going to apply those models for the problem of streamflow forecasting. And then we are going to use those results to get a flood indicator. So as you can see in here, we do this through several stages. The first stage is data processing. We get the hydrometeorological data through the CAMELS data repository. We do some data cleaning, pre-processing, and we have multivariate time series. As I said, we have the precipitation, daily precipitation, and all these features, periodic year, cosine, the minimum temperature, maximum temperature, and the stream flow. These are the multivariate features we have, and the static data, which gives more information about the station and the properties there. So the thing is, like in stage 2, what we do, we just take one of the deep learning models. We take a very simple LSTM model, and we want to kind of first answer a research question, whether it is good to have an individual model batch model, stacked model, or batch static model. And all of these four models have different properties. Individual basically means that you take one station data and you have a single model that is modeling that station, right? And stacked model is basically ensemble stations, a group of stations, and you have batch static and batch, whereas the static is basically combining the multivariate data with the static data. So we have the static data as the also as the input. So further details of each of those are of course in the paper, and we are given the code which shows how this all the data is processed and input to this stage. So once we kind of figure out which one of these strategies are good, we then want to figure out which of the deep learning models are the best for the best strategy. If the individual strategy is the best, for example, then we will apply the deep learning architecture, the four deep learning architectures, and try to investigate which one has the lowest root mean squared error or mean squared error, which are two of our key measurements of error apart from the NSC uh, and SER. So then after that, we now that we have done some very basic groundwork, and actually our first version of the paper, which is in archive, was more focusing on the basic groundwork, and it had less focus on this quantile ensemble model training, which we have incorporated in the revision of the paper. So it's kind of, it could have been two separate papers that was building on top of each other, but we instead had a bigger, better paper. So in there we were like, okay, we just bring the ensemble ideas from the ensemble models, ensemble regression, and then we bring the into an ensemble model training architecture, where we have the historical streamflow and other features as the input, and you take the deep learning with the best catchment strategy, and you train that into your ensemble quantile model, and you predict the stream flow. Then you have the stream flow flood probability indicator. Once your model is trained and you can predict the flood probability indicator, you can apply it to state-wise catchment stream flow prediction, and we then show some cases of some catchments where we show some of those matrices and case studies. Thank you, Arpit. So the CAMELS data set, we have the example of the key static and the time series information, as you see, stream flow and others. Static data, we have the mean stream flow sensitivity to stream flow to rainfall ratio of stream flow to precipitation, and the frequency, average and low and high frequency days. Thank you, Arpit. So the data reconstruction, noted that this is a multivariate time series problem. So you have kind of a history of data of different features. And in time series prediction using deep learning, you need to do something known as windowing or reconstruction. Also, it is called embedding. So the idea is basically you take the data set and you make small windows. So because your data set is not univariate, not one feature, but a series of features, then this is how it looks. You have the data, I know, and after the reconstruction, after you divide into certain windows, you take that as the input, but the output is the day ahead prediction. So let's say that you're interested in multiple days ahead prediction. Then you are going to have let's say a single window is from Monday to Wednesday, the data from Monday to Wednesday, and we want to predict from Thursday to Saturday. So that y is Thursday to Saturday. and Monday to Wednesday is X, and D is the different features. Next slide, please. So Arpit can take from here.
Thank you, Rohit. So as Rohit said, so in stage 2, we evaluate different catchment strategies, which basically is what we are trying to evaluate here is what is the best strategy to train the deep learning model on with respect to the data. So the first strategy that we try is the individual strategy, where we individually process each station separately. We only take the time series data and we do data reconstruction of this data individually. And we train an individual machine learning model to predict the stream flow for that station. Right. So then the second strategy that we try is the batch strategy, where instead of training an individual model for all stations together, since we want to train a regional model, we take stations from a specific state and we train a single model using the time series data on that for that particular state. Right, so we are combining all of the stations in that region, and then we are processing the data together and then training a single model for that region. The second batched approach is the batch static approach, where we also take the static features. So here the static features are also treated just like temporal features, and we do data reconstruction on them as well. And basically the windows contain both time series and the static features, and we train a single model for the region. Finally, we have what is the stacked approach. In stacked approach, we process the static features and temporal features separately. So because static features are not varying in time, we do not apply any data reconstruction, the time series reconstruction of static features. We just process them using a dense neural network. And for temporal features, we use a time series neural network, which is the RNN, the LSTMs, and the CNN models. And then we finally combine the outputs of both these models into what's called the feature embeddings. And then we pass them through a final series of dense layer to generate predictions for these a regionalized model. Right, so when we evaluate these approaches on LSTM using a basic LSTM model, this is the summary of the performance. So we evaluate what is called the squared error relevance score, which is essentially mean squared error, but for extreme values. So what we do is we take extreme values, meaning top 1% values, top 5% values, and so on. And we compute the MSE values for that particular top percentile. And that is reflected in the SER percent values. Right. So, and we also compute the overall MSE for individual projects. Yes.
Right, quick question. Is that the top percentile of actual stream values or predicted stream values? Actuals. Okay.
So basically we have a time series of stream flow values, observations. We select the region where, select the values that lie in that quantile, that top 1% quantile, and we evaluate the predictions against those values. Right, so that's what each of these columns mean. And when we evaluate different strategies, what we understood was that at least for the extreme cases, only the individual model is able to get good predictions. And this could be because there's a large variation in the observed stream flows across the region, which is why training a single model for that region can lead to a more diluted, more averaged out prediction, which leads to you not being able to capture those extreme values. Right. Other than that, we can also see that the batch static model is able to get a very good average prediction performance across the board. But at least for the extremes, we see that only the individual is able to perform very well. So which is why, because we are particularly interested in extreme values, we'll be moving forward with the individual approach for the model. any other thing?
Yeah, I wanted to ask, does that mean the concentration is on the extreme values?
Yes.
More concentration
More
is on the extreme
Yes.
values, not on the prediction.
Yeah, yeah.
Prediction of the extreme value.
Prediction of the extreme value. So we are trying to evaluate how well the model is performing for the extreme values, observed extreme.
Okay.
Yeah, so then in stage 3, we evaluate the neural network architectures for using the individual approach. Yeah. Right, so here is a summary of the architectures that we evaluate. So the 4 architectures on top are the basic standard neural network models from the literature. And on top of that, we also evaluate the quantile-based models, right? So we evaluate the quantile-based LSTM model with tau value of 0.05, which is the 5th percentile model, and a 95th percentile model, right? So we want to get an estimate of how the quantile models perform compared to the standard machine learning models, right? And here is the overview of hidden units. So mostly we've kept the number of hidden units constant. The only place where we are actually changing is for this CNN because this is actually a different architecture. Right, so here is a summary of evaluation only for the South Australia region. So we only consider all the 9 catchments that we have in the South Australia region, and we summarize them in this table. So what you'll notice is that if we look at the rough overall performance of the top 4 models, the overall performance is quite similar across the board. It's not differing by a lot. And even in the case of the SER values, we'll see, we notice that for certain regions, LSTM is performing better, whereas for one example is the SER 75, but for more extreme regions, we see that the BD LSTM is able to slightly outperform the LSTM. So there's not a huge improvement between these models, but there's a slight overall improvement in these predictions. But when we look at the quantile-based LSTM models, we see that the model is actually able to capture better performance in the region that it's trained for specifically. So if you look at the extreme values, which is the SCR 1% and 5%, we see that the quantile LSTM 95 is actually able to perform the best in those regions. Whereas if we look at the lower SCR values, overall performance, the quantile model with 5th percentile quantile is actually performing the best in those regions, right? So towards the right is where this model performs better, whereas towards the left is where this model performs better. So which is why, and since there's not much of a difference in the performance of base models, we're just going to stick with a basic LSTM in the quantile ensemble that we'll be training in the next part. Right, so yeah.
I have a question. For the value, doesn't the quantile LSTM predict the value at the 95th percentile for that specific value?
Yes.
So then,
but what usually happens is that the peaks are actually generally better captured by the higher quantile.
okay. It just seems strange. You're like measuring the error for the top 1%.
Yeah,
but
I get what you're saying. But generally, what tends to happen is that the extreme model, the higher quantile model, which is predicting the upper quantile of the stream flow, is actually able to capture the peak better compared to the standard mean model.
Okay.
Yeah.
Yes.
Right. So then we move on to training the ensemble model. So this slide gives you an overview of the ensemble quantile architecture that we come up with. So essentially, we train 3 LSTM models. The first LSTM model is targeting the upper quantile of stream flow. The second LSTM model tries to target the lower quantile of stream flow, and the regular LSTM is going to target the mean stream flow at that time point. Then we using the confidence interval that we get from these 3 models, we use these predictions and we use some historical flood data for individual catchments, and we come up with a flooding threshold. And that flooding threshold is used to then create a flood risk indicator, which quantifies what is the likelihood of flood occurring at that time level. So we'll be going over those parts in the upcoming slides. Right, so the first part is, in this result, we are trying to quantify the performance of the overall ensemble model, just predicting the confidence interval in different regions of Australia. So we evaluate our model on the top 5 catchments with highest runoff ratio. Runoff ratio means that the catchment is produces more stream flow compared to the amount of precipitation that it receives. And we take top 5 catchments from each region, and we evaluate the model on those specific catchments. Right. So this is to identify what regions the model is able to perform good, whereas where it's not performing as well. Right. So if you look at the average MSE scores in all of these regions, it's approximately coming around the same value. It's 0.3, 5.5. In some catchments, some states, it's actually it's slightly higher compared to the other. For instance, if we look at the Northern Territory, the quantile model does not perform as well as NSW, but the overall performance is still quite relative. Right. So we do this for other states as well. So in WA, in South Australia and Queensland, we notice that the model performs the worst in Western Australia, whereas for South Australia and Queensland, the predictions are more reasonable. Right. So basically what this highlights is that the same model does not work well in all regions, whereas in some regions there is maybe a better model that can be trained depending on the regionalized flow regime. Right, so here is an example of model prediction. So we show examples from different regions. So the first one is from a basin in Victoria. You can see that the 90% confidence interval, which corresponds to the upper quantile and lower quantile model, is able to capture the predicted value in most cases. However, in some high flow regions, it's slightly off. The actual observed value goes outside of this confidence interval, but that is bound to happen because we are only predicting 98% confidence interval. Right. Similar to the above prediction, we have a small region of prediction for Western Australia basin, where we see that in some cases, actually in a lot of cases here, this is a good example of where the model is actually overestimating the stream flow. It's predicting higher stream flow in regions where we do not expect high stream flow. This is just to highlight that although we are able to predict recently, the predictions are not the best out there. So there is still room for improvement in these predictions. Right. So finally, the whole idea of this work is to actually be able to quantify whether a flooding event would happen or not. Right. So we want to actually quantify if the catchment is about to flood at a specific time or not. And when we look at the literature, when I went into the literature, what I understood is that this area is still very murky, right? We don't have very established literature on how we actually quantify floods, right? So this is just one of the approaches that we've taken, but there are a vast number of different types of papers that have come out that have used different approaches to quantify flood. So the approach that we take is based on a flooding threshold. So we start by doing some flood frequency analysis. In flood frequency analysis, what we do is we look at the annual maximum stream flow observed for individual catchments. for those stations. And once those annual maximum events are represented by Q over here. So this gives us maximum stream flow that was observed for that year, and we have a sequence of observed years worth of data. Right, then what we do is we want to quantify what is called the flood exceedance probability, which is represented by alpha. And the way we do it is by ranking these Q values from highest to lowest. And then for each year, we assign the flood exceedance probability as the rank of that year divided by the total number of years plus one data that we have. Right, so this gives us the probability that a flood of that magnitude may occur in the upcoming year. Right, and by using this approach, we can then come up with a threshold for what we quantify as an extreme flood. Right, so to quantify an extreme flood, we have taken a 20% percentile value, but this is again subjective. So what we are doing here is we are looking at the stream flow value that corresponds to the top 20th percentile of this alpha distribution over here. Right. So the way we do it is by looking at again the infimum. This is similar to the CDF function. We are looking at the smallest Q value, which has the alpha value greater than 0.2. Right, and that's what we classify as a flooding event. Again, this is subjective for this research, but more research can be done into to quantify like what is a good value of the exceedance probability that we should look at. Right, so finally, we create a flood risk indicator, which is again a categorical value that utilizes the predictions from the quantile ensemble and the flood threshold to quantify whether there's what kind of likelihood exists for flood in that time period, right? So the Q, capital Q is the prediction, stream flow prediction at that time point, and the key quantiles are represented by small q, and the regular is the standard least squares trained LSTM model. Right, so we have 3 LSTM models that are trained in ensemble. So what we look at is that if the lower bound of the prediction is higher than the threshold, we know that all 3 of those values are above the threshold, and that's what we quantify as a high risk interval. Then in case only the regular value is higher than the threshold, we quantify this as a moderate risk interval. And similarly, if only the upper quantile is higher than the threshold, we quantify it as a low risk interval, right? And if none of them are over the threshold, we consider this to be flood to be unlikely. So that's how we've come up with an indicator. And an example of this is shown in this time series. So we have historical stream flow for Hawkesbury River here in New South Wales. And if we look at the actual values, which are in the red, there are, I think, 4 stream flow events which lie above that flooding threshold. So we are considering, and when we look at the historical flood news data from Hawkesbury River, we see that there was actually a flooding that happened in 2013, earlier in 2013, and towards the middle of 2007. Right, so these actually correspond to flooding events that happened in that region, and we see that the stream flow actually goes way beyond the threshold. Right, so the ensemble model prediction is given in the second plot, and finally we generate the flood probability indicators in the third plot based on the predictions. Right, so if you look at based on that logic, we see that the model does capture this peak very well, and we get a moderate and high flood warning in this region, whereas one of the major peaks which happened in 2013 was not really captured by the model. So this approach works in some scenarios, but there are still there's still room for improvement in certain for certain. Right. Similarly, we have a prediction for the Swan Coast in Western Australia. These were actually some of these events were actually high flow events that led to moderate flooding, and you see that the model is able to capture a lot of these events in the predictions. I think this particular peak corresponds to a flooding event, and which is well captured by this approach. Right. So, Rohit, would you like to discuss?
Right. Thanks, Arpit. So, Arpit has given a very nice presentation about our contributions, the results, and um, as for the discussion, we are summarizing some of the points. Basically, what we need to know, what we investigated, is what was the best strategy from the four catchment strategies. So we found that individual catchment model was the best. It's why is it the best? Basically, it captures the unique local hydrological characteristics. So when you compare the individual with a regional model, with the regional, it means basically you are including other catchment data in one single model. So you have a problem with bigger data set, and actually also you have bigger deep learning models. So that becomes quite difficult in terms of training as well. You will have larger training time, whereas individual models are more calibrated to the local characteristics of the data, and that the training is faster. And although we do want to go from individual to more regional models so that one model takes care of the whole region, that's a desire. But building an ensemble or a group of small individual models is a way to go according to our research. So stacked ensemble limitation, poor performance due to challenges in fusing static and temporal data. That was the limitation. And the batch temporal model uses only the time series data but lacks the tailored accuracy of individual models. So when you compare CNN versus LSTMs, CNNs showed potential for spatial data. They have potential for spatial data, but LSTMs are better suited for streamflow forecasting, according to this study, right? There are other studies such as CNN versus LSTM for univariate time series data, which I did back in 2021, published by IEEE Access. For univariate small data sets, we found that CNNs were better than LSTMs, but this is multivariate data in larger data set, so it's the other way around. So it's you cannot rule out one model. It's good to investigate which one is the best experimentally for now. So ensemble quantile LSTM model performs comparable to conventional LSTM while effectively capturing the extreme values. What we are giving to the market is a model that provides the performance of the individual models, but it is equipped with something more, which is giving you some indication of how likely is that event going to happen. Next slide, please. So conclusions and future directions. So essentially, we have introduced a novel method model. So it's actually more of a framework that kind of fuses, brings together various models together. But in terms of the model development, essentially in terms of the code development, which we didn't really cover in here. And there's also another paper that talks about quantile deep learning models and compares them for time series forecasting. And this paper is kind of based on that. And that paper is also from our group. So essentially, the training algorithm is changed slightly. The model architecture of those deep learning models have been changed slightly. The output layer to develop the quantile LSTM and making it into an ensemble where we are making sure that also the regular LSTM is part of the different types of quantile. So we have the 0.05 quantile and 0.95 quantile, and then we have the regular quantile. And that is what makes it the ensemble. And of course, the best strategy is the individual catchment strategy, and the ensemble quantile LSTM surpasses baseline models by integrating quantile regression. And as the flood indicator part, we've seen for the two case studies that most of the time our models have been doing quite good. But there are some cases where for one of the river basins, it couldn't do as well. So that basically allows us for further research direction. How do we improve those things and probably use better training algorithms, better models? So enhanced uncertainty quantification to integrate Bayesian deep learning for improved probabilistic predictions. So we can use either MCMC sampling, which will be not really not really advisable, but still can be used in principle. Or I think it's good to go the variational deep learning way, which Arpit and I have also done in the past for cyclones. So that could be used to further bring the variational deep learning approaches in this to improve the framework further. And actually, Arpit is going to develop a methodology actually that brings the quantile and variational deep learning together. That's part of his final part of his PhD. So we're going to see more work on that area. Data set, yes, and go further back in history. That's also possible. It may or may not work out. And practical implementations, real time forecasting framework to support flood risk management. Basically, take this to a Bureau of Meteorology in Australia. We need to present this research there and convince them and the government to probably help us, fund us as well, to work onto a solution which could be maybe phone-based Android or Apple apps that can be developed that kind of gives hourly or forecasts so that people are more prepared. Thank you. So the software availability, thanks to Siddharth, Arpit, and my contribution as well. And special thanks to William Verwood, who is not here, and Jim Nung, who have also contributed immensely to this project. The software is all available on GitHub. I'll give Arpit a few minutes to demonstrate the GitHub repository. Thank you, Arpit.
Thanks, Rohit. So the data and the code is available on the following GitHub repository. The source code for all the models is also present in the models.py file, so anyone can easily access this data and code and replicate the results. It should be easy to do. Finally, for different strategies, we have separate training files, and individual training files can be used to train the models. And the overview of these files is also presented here. For the flood risk indicator, we have done it for specific catchments because it was still like experimental in this state. So we provide that as a notebook. So in case you want to look at how the flood risk indicator is generated and the plots are created, you can have a look at this notebook to see how the indicators generated and the plots are replicated. Right. So I think if you have any questions, you can reach out to me. I'm available through my UNSW email, and I'm happy to answer any of the questions. Thank you.
Thank you, Arpit. Thanks, everyone. We can take some questions and comments. We don't have that much of time since we kind of exceeded, so we'll take one or two few quick questions.
Amuchi has a question.
In the last prediction about the Western Australia, please can you on the slide?
Sure.
Initially you said the quantile model didn't do so well in the Western Australian aspects based on the MSE.
Mm-hmm.
But when we went to the prediction, it was able to predict the whole flooding that has happened within that season in dataset used. Like I'm trying to understand.
Yeah.
Here.
Yeah.
He was able to capture this Western. He was able to capture it. But when we went to the MSE, it was performing poor.
Yeah.
The worst in the Western Australia. What could be like the contradiction?
Yeah. So
like be able to predict that. And the last question was supposed to be on the M value. I was a bit confused on why the range was between 0 and 1. The M value in the beginning, because you said doesn't mean it has to be U Y minus U value. Not here.
Perhaps you can share the
CDF.
presentation.
Yeah, in the CDF.
In the definition of the tilted absolute loss function.
Is it? Yeah, about the loss function.
Yeah.
I was a bit confused in the when you talked about CDF, cumulative distribution. Yeah, somewhere down here. Yeah, somewhere here. Like, what does M stand for? Because you said Y is the expected loss function, right? Y minus U is the expected loss function. Then what is M?
So Y minus U represents the U is the predicted value.
Okay,
Y is the observed value. So Y minus U represents the residual. And the residual is plugged as M in this function.
Yeah.
And M can be any real value. So it does not require...
Have to be within the range of 0 to 1.
No. It can be any real value. Tau is what is required to be between 0 and 1 because tau is the actual
Okay, yeah, tau is between 0 and 1.
Yeah.
Okay.
Tau is the percent value, whereas M is a real value. And we want to compute the
that's 100% to 0 to 1.
And to answer your question about Western Australia result, so what we show is only for one specific catchment, but the evaluation results that we showed were for all
the
catchments in that region. Okay. So which is why this is just one catchment, and in this case it seems to be performing okay, but if you still look at these peaks, you see that the model is actually overestimating the stream flow in a lot of these regions, which is what leads to that poor accuracy, prediction accuracy, right? So the catchments here are not very easy to predict for, and because of the magnitude of flow that you see, like it goes up to like 300, which is 300 meters is actually a lot of water. So that corresponds to that high.
Basically, thank you.
Okay, we'll take one more quick question if this.
Okay, I'll jump in. I had lots, but I'll distill it down to one. Thanks, Rohit, Arpit. Great presentation. One thing I wanted to focus on, when you define the actual flood risk indicator, the whole reason you happen to choose that sort of 20% indicator is because actually flooding is underdetermined by stream flow, right? Instantaneous stream flow doesn't tell you actually whether flooding is going to occur or not.
Yeah.
So I wonder if natural extension is, do you want to look at more than just the instantaneous stream flow? And actually it's like, what's the predicted stream flow over a sequence of time periods? So, because it's actually a cumulative event rather than an instantaneous event.
That is exactly what is happening here. But to keep it simple, I skipped that specific part. So the value that we are computing here, it's not actually at one time step, but because we are doing sequence to sequence prediction, we are generating a sequence of stream flow predictions for up to 5 days. And because we know that the flash flooding can happen in a very quick instant and vanish way, so because it's just high peak and down, we've kept that interval small. It's just a 5-day interval, and then we take the maximum over that window, right? So the prediction that you see over here, it's not actually at one instant in time, but it's actually maximum over the next 5 days.
Okay, cool.
And that's what we are
looking
at.
Awesome.
All right, we have a question from Mandana. Thanks. She's saying it's great work. Mandana, you want to ask your question, or should I read it?
Yeah, sure. Thanks, Reed. Great work and nice workflow. Thanks for presenting it. So my only question is that, have you looked at a map of your forecast to see how especially consistent are your results among different stations?
That's a great suggestion, because that's something that we haven't done in this work, because this was already like a very dense work. We have tried out a number of things together. So that is definitely that we can take into consideration for the follow-up work that we'll be doing later.
Yeah, I think the spatial, how good it is, how consistent it is spatially, that will be an interesting extension for this actually. But the thing is that what we are lacking when we're looking at this flood prediction, flood risk indicators, because the data is at a base station, and that base station may not really be close to the river where it is flooding. So those are some of the limitations in these models, and that's why perhaps it is not doing that great as it should at times. So like you could have a couple of kilometer or even 10 kilometer difference between the place where the data was collected, or there's the base station, versus where actually the river is. So these things, like if we have a very fine-grained spatial data set, then doing even a local region, we note that in CAMELS dataset we only have 222 base station, and Australia is huge country, right? So each base station covers a huge distance. So I mean, even for one base station, if we have like fine-grained data set points, then that could make it more possible.
Okay, awesome. So just one more question. And do you think if you have more data set, the encoder decoder will show better result? I'm keen about that one.
I'll just answer that based on our past experience with encoder decoder architecture, comparing these models have been used for crypto price prediction, and that paper is in archive. It's on my profile. And there too, the encoder decoder architecture performed better than LSTM and CNN, and also for multi-step ahead time series prediction. So it is generally better for even small data sets and for the large data sets that we've used in this work. So yeah.
Yeah, I just want to add that for encoder decoder, generally these models are very good for long sequences. They are designed for long sequences, but the data that we are particularly working with, which is streamflow data and hydrological data, the relevance of window is actually very small in this case. Like the streamflow won't be very consistent over very long periods, but there can be like very short peaks, as you see over here as well. Right, so because that window is not very long, even if we use long windows to generate predictions, the accuracy is does not improve very well, right? So which is why these very complex architectures don't produce that great results as we would expect.
Thank you.
Okay, thank you everybody there and online. The next time we will have another presentation after 2 weeks perhaps, and we'll I'll be there later. So just stop the recording and thanks everybody.